Good morning, everybody at home. I'm just trying to figure out what's wrong with the camera.
We can hear you, though, so that's good.
Well, great, thank you. The camera's on, but oh well, everything's on, but the camera won't come on. Oh well, say la vie. We got a black screen until we share the screen. So let's do that. Okay. Well, we've just gone through 3 lectures that talked about competition. Okay, we examined what competition looks like in nature. We looked at some models that help us understand competition and help us predict what's going to happen during competition. And then we looked at the evolutionary response to competition and how it shapes organisms and their niches. We're going to do exactly the same thing for the next interaction, which is exploitation. Now, it's going to take us longer to get through this because exploitation has many more kind of special cases, and we're going to deal with each of the special cases as we get to them. But we're simply going to look today at what predation looks like in nature and what would be necessary for us to understand predation and what kind of models we would have to develop and what kind of things they would have to explain. Once again, we're going to be looking at graphical models here mostly. We'll show you the math that is at the heart of the models, but then mostly we're just going to assume that the math is in the background and we're going to work on the graphs. Now, because exploitation has a lot of special cases, there's going to be a lot more graphs to deal with here. And it's going to be very important for you to try to keep them straight. So again, you'll have practice on these exploitation graphs. Now, why do I call it exploitation? That's probably the first thing to ask. And I call it exploitation because it covers not simply predation, which is how it's usually referred to, but several other kinds of interactions. So in predation, you have a relatively large predator compared to the size of its prey. It must kill its prey and then consume the prey. And a single predator can kill and consume many prey during its lifetime. So that's our typical mental image of a predator. That's a lion eating zebras on the savanna of Africa. That is a mountain lion in the Rocky Mountains eating white-tailed deer. That's a fox eating rabbits. Okay, but that's only one of the kinds of interactions that we're going to focus on here. And the reason that I prefer exploitation is because it applies to it is a general term for any two species interaction in which one species benefits from the presence of the other, while the other species is harmed by the presence of the other. And once again, we're thinking in terms of carrying capacity from the logistic equation. So if a predator has prey, its carrying capacity is increased. It benefits from the presence of its prey. However, if a prey has a predator, its carrying capacity will be reduced. It is harmed by the presence of the predator. So that is kind of our mental image of how these things work, but let's look at a couple of other instances that share the same outcomes. That is, one species benefit, another is harmed, but have very, very different dynamics. So the first would be parasites. Now, parasites steal resources from their host. They're typically smaller than their hosts. There are typically many parasites per host. That's exactly the opposite of predators, where there is a single predator for each prey. And in fact, predators eat multiple prey over the course of their lives. Many parasites occupy a host. Now, the host may die as a result of having too many of its resources stolen, but that's not what the parasite is after. The parasite is not trying to kill the prey. Unlike the predator must kill its prey. A parasite is simply sitting there trying to get enough resources to reproduce. And if it's doing that really efficiently, it might accidentally cause the death of its host. So by that definition, then things like tapeworms are parasites, but also things like grasshoppers eating grass. Those are parasites. They don't kill the grass, they steal resources from it. They eat some of the leaves and then go away. Diseases are all parasites, even the ones that are highly lethal. We'll talk about why highly lethal diseases are really evolutionarily a bad fit, and why this is not really stable. But it'll take us a little time to get there. So diseases, things like tapeworms that we think of as parasites, and things like herbivores, those are all parasites because they all steal resources from a host. They are all smaller than the host. They are all, in many cases, in a situation where there are many of them per single host. And finally, they have no interest in killing the host, especially the parasites that live inside the host. Because if they kill their host, what happens to them? Well, they die.
They die, yeah.
So we're not really arguing that parasites try to kill the host. On the other hand, predators must kill the host, kill their prey. Finally, there's a third category called parasitoids. And these are generally insects that consume their host from within and eventually kill it. Yes. Like wasps. Yes, exactly like wasps. Now, parasitoids are smaller than their hosts. They must be if they're eating it out from the inside. And there may be multiple parasitoids per host. And when we get to food webs, we will talk about not just parasites, but hyperparasites, that is, parasites of parasites. Some of the most interesting food webs around involve these parasitoids, which we call hyperparasites. So mostly parasitoids, thankfully, are limited to two groups, the Diptera and the Hymenoptera, that is flies and wasps. They almost exclusively kill and consume other insects, thankfully. But frequently, you'll go out in your backyard, you'll see a lovely butterfly caterpillar on a plant, and then a day later, you'll see that it seems to have blossomed 30 little white things all over its surface. Well, the caterpillar's doomed. It's going to die because those are the chrysalises of probably wasps around here for the most part. A lot of flies in the tropics, but mostly wasps in places like Louisiana. Now, parasitoids must kill their host. So they're kind of intermediate in characteristics between predators and parasites. Parasitoids must kill their host like predators do. But they're small relative to their host, and there are many of them per host, like parasites. So parasitoids share some features of predators and some features of parasites. It was, fortunately, we don't have parasitoids because they're kind of horrible. The nearest thing to a parasitoid that we might envision is, of course, from H. Geiger's drawings of aliens, which inspired the movie. Can I get a shout out about the movie? Alien, yeah, the movie Alien. The alien has a life stage that is a parasitoid on people. The original movie had John Hurt, who got an egg implanted down in his chest by the alien, which then promptly burst through his chest and ate the rest of the crew eventually by the end of the movie, except for Ripley. And the cat. The cat was a survivor. So that's the nearest thing to parasitoids that we've seen, and you can be very thankful for that. All right, so what we want to do is not focus yet on the different kinds of exploiters here. What we will do first is do exactly what we did for competition. We'll take a tour of what we have to explain about these interactions in nature. Then next time, we will develop some models. And then after that, we will look at the evolutionary responses. So exactly parallel lectures for the first 3 lectures. After that, we will deal with parasites, and we will deal with herbivores as a special case of parasites. And we'll show you how they differ and how they enrich the natural world in many ways. So, oh yeah, gotta go down here. All right, now unlike competition, remember we said competition is ephemeral because it's unstable. And if you have high degree of overlap between the niches of 2 species, they cannot coexist. So we rarely see species in nature kind of actually going at it in competition. Exploitation, we see everywhere. It's everywhere. It's common. It's incredibly powerful. And here's an example. This is a rabbit fence in Australia. This fence actually goes for about 1,500 miles across the length of Australia from Queensland, that is the Pacific coast, kind of cuts off the southeastern part of Australia from the rest. And this rabbit fence then on one side excludes rabbits, and on the other side there are rabbits. And you can see why. Over here on the left, you can see lots of shrubs, you can see tall grass, and over here on the right, you see a lawn. So this is because of the rabbits. The rabbits have done this. The rabbits have structured this environment to the point where many other species can't even exist, like sheep, which is why the fence exists. So we can say thank you to the genius British who brought rabbits because they wanted Australia to look a little more like their country estates outside of London, promptly let them loose and promptly destroyed most of the environment of Australia and restored it only after putting fence up. But here we have one of our clearest demonstrations of the pervasiveness and power of exploitation in nature. So it's everywhere, and we got to understand it if we're going to understand ecology at all. So let's look at how predators and prey, or exploiters and victims, if you will, coexist in nature. Because that was what we tried to do with competition. We tried to lay out, okay, what's possible? There could be extinction, but there could be coexistence. So here is an example of a predator-prey system in which the predators and the prey are coexisting at approximately stable numbers. So stable coexistence. All right, and what we have here is two mites. Okay, and the predator is in the red here, and the prey is in green. And here you see the population density. Okay, now you'll notice that there are somewhat more predators than prey, and that's because the predators are a bit smaller than the prey. So in an experimental arena, when you have both of them together, you're going to wind up with more predators than prey. Kind of like coyotes and white-tailed deer. The coyote's smaller than the white-tailed deer. It is still large relative to the deer, and it still eats many deer over its lifetime. So it is a predator. But here, when you've got them together, they coexist stably. If you take away the predator, what happens to the prey? Whoa, it explodes. Okay. And the only way we're controlling this is by applying pesticides here, where the P is. So every time we get a peak, this fruit grower sprays pesticides and knocks the population way down. So you get these cycles not because of a natural, say, high reproductive rate that is lambda greater than 3.57, but because somebody doesn't like these things and is killing them off with pesticides. So yeah, here we have stability. So predators and prey can coexist stably. So we have to be able to have predator-prey models that have an equilibrium somewhere. It has to be a stable equilibrium. Remember in competition, we had both a stable case and an unstable case. This is stable. So we have to have the equivalent of that in trying to explain predation. Okay, here is one of the most famous studies of predator-prey systems out there, and that's the Canadian lynx and snowshoe hare. Now, the background to this is that these species had valuable fur in the 19th century, and the Hudson's Bay Company sent trappers out to trap them and bring their pelts back to England, where they were fashioned into fashionable clothing. Okay, so they were extremely surprised in the late 1800s to look back at their records and discover that there was a cycle. They did not expect this cycle. But here's the cycle. In the 1850s, snowshoe hares were very common, but then they crashed right around 1865 or so. And the trappers caught very few snowshoe hare. They rebounded very quickly in the early 1870s, but then crashed again. They rebounded at 1875, crashed again, rebounded about 1887, crashed again. So there was this periodic pattern of crashes every few years. And it's approximately an 8 or 9 year cycle. So they were searching for the reasons for this cycle because it looks like a stable limit cycle. And one of them had the genius idea of looking at, say, the lynx pelts, and they found the same cycle. Again, about an 8 or 9 year cycle. And the lynx are in red here, and they're doing the same thing that the snowshoe hares are doing, but they're doing it in a really interesting way. First off, notice that the peaks are not in phase. They're off cycle. Every time you get a peak in the snowshoe hare, the lynx is still increasing. And the peak in the lynx, which is particularly visible right here, this one here, always lags behind the peak in the snowshoe hare. So it's not that they're just cycles. It's that they're linked cycles, and they're linked in a particular way. the prey always peaks while the predator is increasing. And by the time the predator peaks, the prey has already started to decline. And that's really easy to see right here. Here's the peak in the lynx, but the snowshoe hare has been declining for a full 2 years prior to the peak in lynx. So we have a synchronized but not identical set of cycles. They follow the same time period. They're clearly linked somehow. And the way that they are linked is that the prey undergoes oscillations in its population, and when it reaches a peak, the predator is still increasing. When the prey crashes and reaches its bottom, the predator has not reached bottom yet. It is still on the way down. So the predator lags the prey. We not only have to have models that predict a synchronous set of cycles, but they have to predict it very specifically that the predator lags behind the prey. So that's the second thing. We can have stability. We can have what appear to be the equivalent of limit cycles here. We can have extinction. Okay, here's another poor Australia, man. They just really got it bad. This is a photo of cactus that was introduced to Australia, again by some genius Englishman who said, "Wouldn't it be lovely if we could have some flora to increase the diversity of this terribly undiverse continent?" So they brought a bunch of stuff, and one of the things they brought was cactus. And this is just cactus, your standard cactus from the Southwest US, actually. And up top, you can see an entire field that's completely overgrown with cactus. There's so much cactus here that nothing can live there. Kangaroos can't live there. Sheep can't graze there. Cattle can't graze there. They quickly realized that 60% of the entire continent of Australia was covered with cactus. And they thought, oh my God, what are we going to do about this? Well, they imported a moth called Cactoblastis. And I think you can see that the name is, pretty accurate, Cactoblastis. And sure enough, it blasted that area. And every cactus plant here is extinct. So predation or exploitation can also cause extinction of the prey. We must be able to have models that allow that to happen. Of course, what happens to the predator when the prey go extinct? Well, what are they going to eat? So they go extinct too, at least locally. So that's kind of a problem for the predator. But, and as you'll see when we talk about the evolutionary response, why that doesn't happen more often. So we can have stable coexistence. We can have what look like limit cycles. We can have extinction of the prey and later on the predator. Now, we can also have coexistence of the predator and prey that cycles under conditions where you'd expect extinction. So you'll remember that mite experiment that we talked about a little while ago. Well, that's just one of many predator-prey systems. If you put a different set of mites on an orange, one of the mite species will suck the juices of the orange rind and will be very happy and will reproduce. But if you put a predator of that particular species on the orange, it will eat every single mite and cause the extinction of the population. Okay, well, that's a straightforward case that's equivalent to cactus and Cactoblastis. Predators cause the extinction of the population. But this man Huffaker at UC Berkeley realized that yeah, well, we don't see that in nature. What we see is that, yes, mites go extinct on a particular orange, but they are present at all times on the tree, on other oranges. So how does that work? How do they stay ahead of their predators? If their predators are driving them extinct on one orange, can they disperse to another orange before the predator can find them? So what he did was a series of experiments. And of course, because mites are tiny and he didn't want to look at that many mites, he wrapped an orange, mostly in wax paper, and just left a little bit available for the mites. He divided the orange into sections with a ballpoint pen so he could count the number of mites in each little section. And that gave him a much easier way to study the numbers of the predators and the prey. So he knew that if he just had the mites on one orange, that the predators would drive the prey extinct. So he said, what if I simulate an orange tree? So here's his simulated orange tree. It's actually an array here of 120 possible food positions. Okay, the white spaces are blank. Okay, the orange spaces are whatchamacallit, are moderate are moderate densities, and the red are high densities. Okay, and what he did was intersperse some of these positions with rubber balls. So there was nothing to eat there, but it was possible for the mites to crawl across the balls and disperse. And here's what happened over time. So over the course of about 8 months, he saw limit cycles. Now this is interesting because we know that on any given orange, the predator will drive the prey extinct. However, in the entire system, the predator could not drive the prey extinct because they were dispersing ahead of the prey. And basically, they had what amounts to a refuge. Every time a predator would colonize one of these, like right here, every time the predator would get into a population of mites, the mites are continuously dispersing all over this array. And by finding another orange a few oranges away, they could escape their predator. And they could establish a new population that the predator would have to then find. So again, the predatory mite is generally, let's see here, six-spotted mite. Yeah, six-spotted mite is the prey. So we have what amounts to limit cycles, and we have the prey peaking before the predator. Again, the predator lags the prey. But this time, it's not any sort of stable thing. It's because there is a refuge. There is a way to escape. So in systems where predators could normally drive prey extinct, if we allow the prey to have a refuge, they will not go extinct. They will cycle forever. So that's kind of a special case of our limit cycles. This is not something you'd actually expect without the refuge. Without the refuge, these guys are toast. They're going extinct. With a refuge, you get cycles. So that's a special case, and we need a special way of viewing that, different from the way we view the lynx and the hare. Okay, so that's our challenge then. We need to have a way to model, first, stable coexistence. Second, limit cycles, specifically in which the predator lags the prey. Third, our models must be able to allow extinction. And fourth, we must be able to put a refuge in our models so that the predator cannot drive the prey extinct, even though it normally would be able to do that. So that's our challenges for our models. And what I'm going to do now is begin to develop those models. And I'm not going to go very far into this, but I'm going to set us up for next time. Okay. So the people who took this seriously and first tried to develop models of predator-prey interactions, because they weren't really focused on parasites or parasitoids, were two Italian scientists named Lotka and Volterra. And in fact, when we talk about the logistic equation, when we talk about competition equations, those are also due to these guys, Lotka and Volterra. So they were very, very influential, and you'll come to hate them even more than you do now. But they were the ones who started toying with this idea, trying to develop a way to predict how predation in particular would work. So they messed with the logistic equation for a long time, a couple of years, as it turns out, from their notes. And they ultimately decided, this was just way too complicated. We cannot modify the logistic equation to make any sense of this. It's just too convoluted. So they threw it all out and made some other assumptions. First, they said, well, let's just look at the very simplest case possible. Let's assume that there's no competition within the prey. So they'll grow exponentially. Let's also assume that there's no competition within the predator. So that right there, that throws out the logistic model. And then let's make a couple of other assumptions. When we're looking at the prey, let's assume that the birth rate is constant. And let's say that every single prey that dies because it's eaten by the predator. Okay, that simplifies things really a lot. We don't have to deal with competition. We don't have to deal with anything except how many predators there are to eat those prey. And let's see how far we can get just with that assumption. So their assumptions for the prey are that there's no competition among the prey, that birth rate is constant, and that death rate depends on predation exclusively. Okay, and that's going to have some of the elements of the logistic equation, but not all of them. Now let's think about what the predator should do. Well, the birth rate of the predator should be exclusively dependent on the number of prey. So if you have a certain number of prey available, the predator should be able to reproduce. If you have less than that, the predator should go extinct. And let's just say, oh, well, let's not deal with the death rate of the predator. Let's just say it's got a constant death rate. And just whatever that is, let's just call it D. Let's call it a death rate. So in this formulation, which is now quite unlike the way we were thinking about competition, the victims are exclusively controlled by the predators. And the predators are exclusively controlled by their prey. So this is really unrealistic, isn't it? Because, of course, many, many, many things affect birth rates and death rates. And it's unreasonable to think that competition doesn't occur. But let's just see how far we can take this little model. So we're going to call these guys exploiter and victim, or as Locke and Volterra did, we'll use N to refer to prey and P to refer to predators. You can see how other people have referred to this in scientific papers. But we're going to make the number of prey always on the x-axis. The number of predators is always going to be on the y-axis. So let's see if we can finish formulating this before we have to quit today. So let's consider the prey population. Well, dNdt of the prey is going to equal the births minus the deaths, right? That's just another way of thinking about population growth, the logistic equation. We're just substituting simpler terms. So what we need to know is, well, what's the birth rate? Well, that's just Rn, because it's the exponential rate of growth times the number of individuals reproducing. That's the birth rate. Okay, so far, we're not too far away from what the logistic equation looked like. But now what's the death rate? Okay, we didn't really deal explicitly with the death rate when we talked about the logistic equation. We just said, well, the rate of population growth slows, but we didn't talk about a death rate. And now, because we are looking explicitly at births minus deaths, we need to have some way of estimating the death rate. And here's where our assumption comes in. We're assuming that every individual dies because they got eaten by a predator. All right, well, that allows us then to make the following thing. We're going to say that little p is the rate at which individual prey are killed by an individual predator. So there may be a 1 in 1,000 chance that an individual prey is killed by that individual predator. And then here's the number of prey in the population. And here's the number of predators. So if each prey has little p probability of being killed by a predator, and there are p predators, then the death rate for the population is the number of individuals in the population times the rate at which they're killed by predators times the number of predators. Little p times n times p. So this is our substitute for the logistic equation now. It's dNdt equals R times N, that's the birth rate, minus P times N times capital P, the death rate. So we've used some of the ideas in the logistic equation, but we haven't tried to modify it directly. We've extracted those ideas. We just got a birth rate and a death rate. The birth rate is R times N. The death rate is P times N times P. Well, what can we do with that? Let's consider the predator population and get the other equation for the other species. So once again, we have a birth rate and a death rate. Births minus deaths gives you the rate of change in the population over time. Now, the birth rate depends exclusively on the ability of the predators to catch their prey. And we already know what that is. It's P times N times big P. But just because you catch one doesn't tell you how efficiently you convert a dead prey into a baby predator. Maybe you have to eat 100 prey before you can reproduce one time. So there's a conversion rate here. That's little a. That's the rate at which one prey is converted into one predator. If you need 10 prey to make a baby, then the rate is 0.1. If it's 100 prey, then it's 0.01. Actually, quite straightforward. So this is the rate at which predators catch their prey, little p times N times P. And here's the rate at which those prey are converted into baby predators. So that's going to be the birth rate here. And we said that the death rate, they just die. They just die, and there's a constant death rate. So the rate of deaths in the population depends on the number of predators in the population, that's P, times the death rate, P. So this is our equivalent equation for predators. So in both cases, we have some elements of the logistic equation. It's really obvious in prey, less obvious in predators, but we're not actually working directly with a logistic formulation. So what do we do with them? Well, what we want to do is get isoclines. So let's look at what the prey population isocline would look like. So remember, we want to set dNdt to 0, which is the point at which the number of predators and the number of prey that forces the growth rate to go to 0. So if we set it to 0, then births will exactly equal deaths. So dNdt equals this. And I wrote it backwards because I like the consistency here. Okay, so Rn is the birth rate minus the death rate equals dNdt, and we're setting dNdt to 0. So let's just rearrange. Well, let's add P and P to both sides. Okay, that cancels out. And now we have Rn equals P times N times P. You have N on both sides. That cancels out. So now little r, the birth rate, equals the predation rate times the number of predators. And dNdt equals 0 when the birth rate divided by the predation rate equals the number of predators. All right, that's completely bonkers. That is so weird because the 0 growth isocline of the prey population depends exclusively on the number of predators. It has nothing to do with the number of prey. Mathematically, that's what we get. Logically, that's kind of about as strange a result as I can imagine. Not only that, but it's a constant number of predators. It's R, the birth rate, divided by P, the predation. When the number of predators equals the birth rate divided by the predation rate, you have the prey population that does not grow. Well, here's a problem with this. It's a constant. R divided by P is a constant. So that means we've got a really weird looking graph. That's our graph. The 0 growth isocline of the prey doesn't even touch the prey axis mathematically. So here's our predators on this axis. Here's the number of predators that causes the prey population to stop growing. And here's the prey axis. So in the basic Lotka-Volterra model, this isocline doesn't even touch the prey axis. I've always found that to be so weird. And I've always found it to be hard to convince people of. But just bear with me because it's going to do some interesting things for us. Well, what that means is that if the predators are less than this number down here, then the prey can increase. And so they will just increase from left to right. If you have more predators than that, then the prey must decrease, and they will decrease from right to left. So you have a system of arrows going from left to right and from right to left. And there it is. And that's because we made the assumption that there's no density dependence, that predators control the prey exclusively. So this is what we get out of that basic model. So look at the predator population. We'll finish up with the predator population today. So once again, we're going to set births equal to deaths in order to generate an isocline, a zero growth isocline. And that means that dp dt, the number of change in predators over time, will be zero. So dp dt should equal zero. Births should equal deaths. So let's do exactly what we did with the prey isocline. And so here's our equation. And of course, what I did was put dp dt over here for simplicity's sake because it's easier to rearrange. But we're making it zero. So add the death rate of the predators times the number of predators to both sides. That cancels this. And then you have AP NP equals DP. What have you got on both sides? E. Cancel P. And now you have AP times N equals the death rate of the predators. And dP/dt equals zero when the number of prey equals the death rate of the predators divided by the predation rate times the conversion rate. Okay, but that's also extremely strange because the predator isocline has nothing to do with the number of predators. It only has to do with the number of prey. And that number of prey is constant. It's the death rate divided by the predation rate times the conversion rate, D divided by AP. So once again, we have a really weird result. And what does that do for us? Well, here it is. Here's the predator isocline, and it's straight up and down because it's a constant. D divided by AP is constant. And the predator isocline never touches the predator axis. It intersects right here and it goes straight up. If you have this many prey on the right side, you have enough prey for the predators to increase. So they will increase from bottom to top. If you have fewer prey than that, they will decrease from top to bottom. Too weird. Now, at this point, you should say, mathematically, I see how you got that. That doesn't make any sense whatsoever. And it was the genius of Lotka and Volterra to just hold off and to just keep checking. What would this imply? If you put them together on the same graph, two things emerge. First, you have stable equilibrium. That's one of the things we were looking for. What else do you have? Well, let's examine what happens here. On this lower left, the predators are decreasing. And because you're below the prey isocline, the prey are increasing. So the net movement of a combination of predators and prey down here will be that way. Once you get across this line, then the predators can start increasing because there are enough prey. The prey are still increasing, so you go down here, but then you switch. You go up. If you cross this isocline, now you have too many predators and the prey have to decrease, but the predators are still increasing. So you go this way, this way, this way, and this way. And you get stable limit cycles. You get stable limit cycles. Now, this looks kind of like a stable equilibrium. It's not actually a stable equilibrium because if you do something to push the populations off of it, there's no way for them to get back. They just start cycling indefinitely. So this is still not really what we're looking for. But hey, this is about as stupid a model as you could possibly imagine. And it got us 2 of the 4 results that we're looking for to explain all predatory interactions in nature, which is not bad for something that is just terribly, terribly simple. Notice one other thing before I let you go. Remember we said that we had to have cycles and we had to have a particular type of cycle. We had to have prey reaching their maximum before the predators reached their maximum. Well, look here. The prey are going to reach their maximum here, right about there. That's the maximum number of prey. But look, the predators can still increase when you cross that line. So the prey reach their maximum while the predators are still increasing. And the predators reach their maximum here after the prey do. Not only do we have limit cycles, we have the right limit cycles. The predator lags the prey. Bingo. We don't just have two important results. We have two important results, and one of them is really impressive for such a simple model that makes what sounds like crazy assumptions. So I'm going to end this here. Ask if there are any questions before we go. We will pick up on this Lotka-Volterra model next time. I'll run through it quickly again when we start, and then we'll move on to see how ecologists have actually modified it. Because this is the basis of our modern understanding of predator and prey. Hey guys, I will stop this unless you guys at home have any questions. All right, well, I will see you later.